My name is Dan Ricketts, and I'd like to tell you about automating formal proofs for reactive systems. Let's start with some motivation. So there's a verification technique in which you implement and formally verify your software in a proof assistant. This has been around for a few decades, but it's really gained momentum in the last 10 years or so. There's a lot of excitement about the possibilities, and I think this excitement is really justified, especially based on the results of a study published at this conference a few years ago. So the authors of this study built a tool for randomly testing C compilers, and they ran their tool on a number of modern, widely used compilers to try to find bugs. So they ran their tool on GCC, they found 122 bugs. They ran their tool on LLVM, they found 181 bugs. And then they ran their tool on CompCert. Now CompCert's a little bit different than the others. CompCert was implemented in a proof assistant and proven correct in full formal detail. And when the authors ran their tool on CompCert, how many bugs did they find? 0. They found no bugs. Well, actually that's a lie. They found a handful of bugs, but all the bugs they found were in the unverified portions of CompCert, and since publication, those portions of CompCert have been verified and those bugs no longer exist. And in fact, this is still true in 2014. Just yesterday, Vu told us how he had tested CompCert for a year using a tool that found hundreds of bugs in GCC and LLVM. And using this tool, in the verified portions of CompCert, he again found no bugs. That's amazing. Bug-free software. Why aren't we implementing all of our software in proof assistants? Well, before I answer that question, I'm going to give an overview of how proof assistant-based verification works. Then I'm going to return to this issue that's preventing its wider adoption. And finally, I'm going to talk about the approach that we developed to try to address this issue. So in proof assistant-based verification, you first select a proof assistant, like the Coq theorem prover. You write your code in the language of that proof assistant. You write a specification characterizing how your code should behave. Then you hire a team of grad students, or Xavier Leroy, to interact with the proof assistant to show that the code satisfies the specification. And finally, you compile your code down to some executable form, and in the end, you obtain these extremely strong guarantees about the code that actually runs. As I've already said, this has been used to build a C compiler. It's also been used to build the microkernel of an operating system, and the kernel of a web browser, and a handful of other systems. But it hasn't been widely adopted. And why not? Proof assistants give us extremely strong guarantees about our software. Why aren't we implementing all of our software using proof assistants? Well, there's a catch. For all of these systems, the vast majority of the manual labor is devoted to proofs. That is, the vast majority of the manual labor is devoted to interacting with the proof assistant to show that your code satisfies your specification. And to really emphasize this point, I want to focus on just one of the systems I just mentioned, the microkernel of an operating system, Cell 4. So this microkernel consists of just 9,000 lines of C code. And yet to verify these 9,000 lines of C code, to show that they satisfy their specification, it required 20-person years of labor. 20-person years for verification. And in fact, the situation is even worse than these numbers indicate. Not only is a massive amount of manual labor required for proofs, but this labor must be done by people with deep expertise in proof assistants. And once you spent all this time writing your proofs, if you change anything in your code or specification, you frequently have to update many of your proofs because proofs tend to be extremely brittle, and this creates a big barrier to maintenance. So what would the ideal situation be like? Well, in an ideal world, we wouldn't have to write any proofs manually, yet we'd still obtain the extremely strong guarantees provided by proof assistants. Well, in this talk, I'm going to tell you about an approach that we developed to achieve this ideal situation for a number of different programs. So the key idea to our approach is to isolate a single application domain with a number of different programs. And we observed that within a single application domain, the specifications tend to contain similar properties, the code tends to follow a similar architecture, and the proofs tend to follow similar patterns of reasoning. And what this suggests is that we could have a domain-specific language for specifications, a DSL for code, and automation that captures these common patterns of reasoning. And so a user of such a system simply has to write the code and specification for a program, then send this code and spec through the proof automation, and the proof automation outputs fully machine checkable proofs, giving the user the same strong guarantees provided by proof assistants without requiring the user to write any proofs manually. And so we instantiated this idea in the domain of reactive systems, which I'll define next slide. And we built a tool called Reflex, which consists of a DSL for implementing reactive systems and specifying their properties, plus automation to show that user-provided code satisfies user-provided properties. Now we implement it as a DSL embedded in Coq, yet we don't require the user to write any manual Coq proofs. In fact, we don't require the user to know anything about proof assistance whatsoever, yet the user still obtains the extremely strong guarantees provided by proof assistance. Now the automation is incomplete, which means there are certain properties expressible in Reflex which the automation cannot handle. However, we use Reflex to build the kernel of a web browser, the kernel of an SSH server, and the kernel of a web server. And moreover, we use Reflex to specify many important properties of these three systems. And our automation was able to handle every single one without any manual intervention. And this shows that the automation works well in practice. And moreover, this is a modern web browser and a fully featured SSH server. And to convince you of this, at the end of this talk, I'm going to show you a video of our browser and SSH server in action. So now I'd like to talk about how Reflex works from the perspective of a user and how the automation works at a high level. But first, as promised, let me give an informal definition of a reactive system. So a reactive system is one which communicates with outside components by continuously reading messages from components and sending messages to components. And so an example of such a system is the kernel of a web browser modeled after the Google Chrome architecture. So in this architecture, each tab runs as a separate sandbox process, and for each domain on which a tab is opened, there's another separate sandbox process that stores cookies for that domain. And finally, there's a single kernel which mediates communication between these components and provides access for these components to outside resources such as the network, user input, and the screen. And so an example interaction, a tab might request the value of a cookie by sending a message to the kernel, and the kernel, subject to certain access controls, might retrieve the value of that cookie from the appropriate cookie manager and send it back to the requesting tab. And so we actually implemented this kernel in Reflex, and I'd like to show you how that works. So to implement the kernel of a web browser in Reflex, the user first writes the types of components with which the kernel can interact. So the kernel of a web browser can interact with tabs, cookie managers, and so on. Next, the user writes the types of messages that can be exchanged between the kernel and outside components. So there's a message type for setting the value of a cookie, a message type for retrieving the value of a cookie, and so on. And finally, the user writes how the kernel responds to messages from components. So for example, when the kernel receives a cookie set message with value C from a tab, the kernel first retrieves the cookie manager for that tab's domain using the find command. Now the find command is simply a primitive of Reflex, and in this case, the find command first tries to retrieve the cookie manager for that tab's domain if one already exists, and if one does not already exist, the find command simply spawns a new one. In either case, once the kernel has the cookie manager for that tab's domain, it sends this cookie manager a cookie set message with value C. Now that's the end of that handler, and of course there are many other handlers for other message types and other component types. So now what you have on your screen is all that a user has to write to implement the kernel of a web browser. Now how does a user specify the properties that this kernel should satisfy? That is, how does a user specify the allowed behaviors of this kernel? Well, in the case of reactive systems, the user specifies the allowed behaviors with respect to the sequence of system calls that the kernel can make. And to illustrate what this sequence looks like, I'd like to focus on just one handler and tell you what system calls are made when that handler is run. So now let's suppose the kernel's been running for a while and has made a number of system calls so far. And then the kernel receives a cookie set message from a tab. Well, receiving a message from a tab corresponds to a system call. Then the kernel retrieves a cookie manager for that tab's domain. Now let's suppose that one does not already exist, and so a new one must be spawned. Well, spawning a new component corresponds to another system call. And finally, the kernel sends a cookie set message to the cookie manager. Well, sending a message to a component corresponds to yet another system call. So these are the three system calls that are made when this handler is run. And more generally, the sequence of system calls can be broken up into a sequence of handler executions, each of which makes some number of system calls. So that's what the sequence of system calls looks like. Now, how does a user specify properties that this sequence should satisfy? Well, I'll illustrate this with another example, in particular, cookie integrity. So cookie integrity is a property that cookies cannot leak from a tab to a cookie manager of a different domain. And so to specify this in Reflex, a user simply writes that for any domain D and cookie value C, the kernel sends a cookie manager for domain D a cookie C only if the kernel has already received the same cookie value C from a tab of that same domain D at some point in the past. And so note that to specify this property, the user uses the enables primitive, which is simply a primitive of Reflex. And more generally, we say that A enables B if and only if every system call B is preceded at some point in the past by a system call A. Now, enables is just one primitive of our specification language. And more generally, our specification language is a strict subset of temporal logic. And I'll talk about that a little bit more towards the end of the talk. So now what you have on your screen is all that a user needs to write to implement the kernel of a web browser and specify cookie integrity. Then the user sends his code and specification through the proof automation, and the proof automation outputs a fully machine checkable proof that this kernel code satisfies cookie integrity. I think this really highlights the benefits of Reflex. In particular, proofs are fully automated. This means that the user doesn't have to write a single lemma, the user doesn't have to write a single invariant, the user doesn't have to write a single line of manual proof, and yet the user still obtains the extremely strong guarantees provided by proof assistance. Now, how are we able to achieve that level of automation? Well, now I'm going to talk about how the automation works at a high level. So the goal of the automation is to show that user-provided code satisfies user-provided properties. And the automation does so by induction on the sequence of system calls that the kernel can produce. Now you might recall that this sequence of system calls can actually be broken up into a sequence of handler executions, each of which makes some number of system calls. And this sequence of handler executions actually creates a very natural structure for induction. And so the automation actually performs induction on this sequence of handler executions. And what does that look like? Well, the automation has some induction hypothesis stating that the user-specified property holds up to some point in the execution of the kernel. And then a single handler is run, and the automation must prove that the user-provided property still holds after this single handler was run. And how does the automation do so? Well, it first performs case analysis on which handler was run, and then for each possible handler, the automation symbolically executes all possible paths through that handler, and for all possible paths, the automation attempts to prove that the user-provided property still holds. And how are we able to achieve this level of automation? Well, the key was isolating a single domain, and in particular, that gave us the following insights. First, we carefully designed our property primitives, such as enables, to be expressive enough to capture many important properties of reactive systems, but simple enough to enable significant automation. And second, we observed that for the reactive systems we considered, it was sufficient for handlers to be loop-free. That is, no loops within handlers. And by restricting handlers to be loop-free, this allowed the automation to symbolically evaluate all possible paths through a given handler. And finally, you may have noticed that the property I showed, cookie integrity, was a relatively simple property that required reasoning about only a single handler. However, our automation is more sophisticated. Our automation can actually reason about sequences of handlers. And in order to enable this non-local reasoning, we identified certain common programming idioms in the domain of reactive systems, such as guarding access to a critical resource using some global variable, and we use these idioms to implement certain heuristics in the automation to enable non-local reasoning. Now the automation is incomplete. However, I'd like to convince you that the automation works well in practice. So we implemented 3 kernels: the kernel of a web browser, the kernel of an SSH server, and the kernel of a web server. And we also implemented the kernel of a hypothetical car controller, and for more details, you can check out the paper. Across these 3 systems, we specified a total of 33 properties, and the automation was able to handle every single one without any manual intervention. Now, 80% of these, the automation handled in less than 2 minutes, and the slowest one took around 9 minutes. And here are some examples of properties the automation was able to handle without any manual intervention. I'd like to focus on just a couple of them. First, in addition to the temporal logic primitives that I talked about, we also have a primitive for specifying non-interference. And for the kernel of the web browser, we use this to specify that different domains do not interfere with each other. And the automation was able to handle this without any manual intervention. And second, for the SSH server, we specified that the SSH client is not granted access to a pseudo-terminal for a given user before successfully authenticating as that user. Now this is actually a non-local property. That is, it requires reasoning about sequences of handlers. And our automation was able to handle this non-local reasoning without any manual intervention. Now I'd like to convince you that Reflex saves development effort. So the Reflex implementation consisted of around 7,500 lines of code, and this allowed us to implement the kernels of 3 different systems. Any user of Reflex could potentially implement additional kernels. Now I'd like to focus on just one of these kernels, the kernel of a web browser. So the kernel of a web browser was previously implemented manually in Coq, and this development consisted of around 5,500 lines of Coq code. And all of that development effort resulted in the verification of just a single reactive system. And yet for roughly the same development effort, Reflex enables the verification of many reactive systems. So that's the development effort required to build Reflex. Now what about the development effort required to build systems using Reflex? Well, this table gives a number of lines of code and specification for the kernels of each of our 3 systems. It also gives a number of lines of code required to implement the surrounding components for each of these 3 systems. Now you might notice that the kernels are relatively small, but keep in mind that these kernels perform the critical functionality that we needed to verify. You've probably also noticed that the surrounding components are relatively large, but keep in mind that we did not build these components entirely ourselves. Instead, we built upon existing frameworks like WebKit for the browser and OpenSSH for the SSH server. Now there are some limitations to Reflex, and these generally fall into 2 categories. First, expressiveness. Our specification language consists of a primitive for non-interference and a number of primitives that make up a strict subset of temporal logic. And most significantly, these primitives do not allow nested temporal logic expressions. Second, as I've already said, we require handlers to be loop-free. That is, no loops within handlers. Now, we didn't find this to be a significant restriction for the reactive systems that we considered, but we can imagine that for other reactive systems, this might be a restriction. And finally, we do not allow the user to define unbounded data structures within the kernel. Now, the automation is incomplete, and this is primarily for 2 reasons. First, the automation is unable to infer certain inductive invariants. For example, the automation cannot infer that some global variable increases monotonically. And second, we implemented our automation in the tactic language LTAC, and this actually leads to some low-level incompleteness in our automation tactics. So as I've already said, we built the kernel of a fully featured SSH server in Reflex, where the main property we verified is that a user is not granted access to a pseudoterminal before successfully authenticating. I'd like to show you a video of this server in action. So here we have Don logging into our SSH server. He's going to pull up an Emacs buffer with a Reflex source file. He's going to do some editing. You'll notice that Emacs is responsive. It's actually responsive enough to play some games. So here we have him playing some Snake, and he's going to play some Tetris as well. And now we have a video of our browser in action, whose kernel we implemented and verified in Reflex without writing any manual proofs. You'll notice that the browser is responsive. Now keep in mind that all communication between components and all access to outside resources is mediated by the kernel. This means that every keystroke, every mouse event, every network request, every cookie request, every write to the screen is mediated by the kernel and automatically verified to satisfy our safety and security properties. Yet the browser is still responsive. Now this is partially because we adapted some optimizations for Google Chrome, like rectangle-based rendering. Now you may have noticed that Don did not have to enter any credentials to get to Gmail. This is because cookies work in our browser, and not only are they functional, but they're automatically verified to not leak from one domain to another. You may have also noticed our address bar is a little non-standard. This is because we implement it as a separate component so that all address bar changes can go through the kernel. Of course, you can use our browser to render more than just Google sites. Here we have Don playing some more Tetris. Guy really loves Tetris. Of course, you can do some shopping as well. Don's pretty excited about the World Cup. So I think here he's actually going to pick up a soccer jersey of the next World Cup champions. Good choice, Don. Now I'd like to conclude by showing where our work stands in relation to other work on proof assistance. I think this is best demonstrated with a plot on your screen. There's often a trade-off between the expressiveness of a tool and the level of automation it provides. And so in the beginning, there were systems like Coq, which provide extremely expressive languages with relatively low level of automation. And since then, there's been work like Why Not and Bedrock, general purpose verification frameworks, which begin with very expressive languages and try to push the automation as high as possible. And we took a different approach. We began with a very inexpressive language with a high level of automation, and we tried to push the expressiveness as far as we could while maintaining this high level of automation. And we were able to push the expressiveness far enough to implement an entire domain, in particular reactive systems, and yet we kept the automation high enough to completely eliminate the manual proof burden for many important properties in this domain. Now, if you'd like to learn more, we have a project webpage which contains our paper, our source code, and a virtual machine image that you can download to run all of the systems which I've talked about today, and perhaps implement one of your own using Reflex. Thank you.